Today I'm going to be talking about modeling with exponential and logarithmic equations, Chapter 7, Section 7. So first off, we need to determine the type of function represented by the table. So we have a table of values, and if you remember, we're going to find a pattern of the y values, either the differences or if it's multiplication or division. So if we look at this first one, I notice that 0.5 times 2 is 1, 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, and 16 times 2 is 32. If there is a common pattern of all multiplication or all division that is a common factor, the same number, then it's going to be exponential. If we look at this next one, there's nothing that we can multiply that comes out to be the same number, so we can take differences. 0 minus 2 is a negative 2, 2 minus 0 is 2, 8 minus 2 is 6, 18 minus 8 is 10, 32 minus 18 is 14, and 50 minus 32 is 18. Now, if all of these were the same and be a first difference, it would be linear, but it's not, so we have to take our second differences. 2 minus a negative 2 is 4, 6 minus 2 is 4, 10 minus 6 is 4, 14 minus 10 is 4, and 18 minus 14 is 4. Since these second finite differences are all the same number, this is a quadratic function. All right, let's look at another example. Same thing, let's look at these. I usually look to see if it can be multiplied or divided by the same number. These cannot. They all can be subtracted by 3. Since all the differences are the same on the first finite differences level, this is a linear function. If we look at this next one, everything can either be divided by 3 or multiplied by 1/3. If that's the case, that is exponential. Next up, what we're going to be doing is we're going to be writing exponential functions using the model y equals ab to the x, whose graph passes through the given points. So I'm giving you 2 points. I'm going to label that x and y, x and y. And what we're going to do is we're going to plug these numbers into y equals a times b to the x. So the first one is 6 equals ab to the first, and the second one is 54 equals ab to the third. So now we have a system of equations. So what we can use is we can use substitution. I'm going to solve for a. To solve for a, it's going to be 6 over b because we divide by b. And we can substitute in 6 over b for the a in the other equation. So we can make this 54 equals 6 over b times b cubed. If we simplify this, this becomes 54 equals 6b squared. And then what we can do now is we can divide by 6 and get 9 equals b squared. So b is equal to 3 if we square root both sides. Now remember, your a value is allowed to be negative because that shows a reflection, but b is always positive. Now that we know b is 3, we can plug in for a. So we get a is 2. So we now can write our equation, y equals 2 times 3 to the x. All right, let's do another one. Let's label our x and our y. This is going to be 12 equals ab squared. And then the other one is going to be 24 equals ab cubed. Let's solve for a. So a is going to be 12 over b squared. We're going to plug that in. 24 equals 12 over b squared times b cubed. 24 will equal 12b, so b will equal 2. We can plug that back into a equals 12 over 4, which is 3. So now we can plug that into our equation, so y will equal 3 times 2 to the x. And that's our exponential function. Let's try 2 more of these. Okay, we have 1, 2, and 3, and 32. Label. We're going to plug in. 2 will equal AB. 32 will equal AB cubed. Let's solve for A, which is going to be 2 over B. Plug into the other equation. 32 equals 2 over B cubed. Simplify, 32 will equal 2B squared. If we divide, 16 will equal B squared. B will equal 4 when we square root both sides. When we plug back in, A will equal 2 over 4, which simplifies to 1/2. So our exponential function is y equals 4 times, so 1/2, that's our A, times 4 to the x. All right, let's do our last example for this. We're going to label and plug in. So we have 16. Let's do that in red. Equals AB squared. And then 2 equals AB to the 5th. We're going to solve for A, which is 16 over B squared. We're going to plug that in. So this is going to be 2 equals 16 over B squared, B to the 5th. We simplify and we get 2 equals 16B cubed. We divide by 16 and get 1/8 equals B cubed. We have to cube root both sides, don't forget. So B will equal 1/2. We're going to plug that back into here and we get A equals 16 over 1/2 squared, and we get 64. So we're going to write that exponential model as y equals 64 times 1/2 to the x. So that's how you write your exponential functions. We have one word problem to go over. It's very similar to what we've been doing. It says a store sells trampolines. The table shows the numbers y of trampolines sold during the x year that the store has been open. Write a function that models the data. Do you think this model can be used to predict the number of trampolines sold in the 15th year? So what we're going to do first is we're going to pick 2 points. I'm going to pick these first 2 and plug them in. So I'm going to get 12 equals A times B, and then 16 equals A times B squared. Do the same thing as we did before. A equals 12 over B. Plug in. 16 equals 12 over B times B squared. 16 equals 12B. B will equal 4/3. Plug that back into, and that will equal 9. So our model is y equals 9 times 4/3 to the x. Now it is possible to predict the number of trampolines sold in the 15th year, but it's really not logical or probable because when you're a business, you don't keep on selling more and more and more trampolines. So for the 15th year, it is a little too far out to predict, so no, you can't use the model to predict the number of trampolines sold in the 15th year.